I'm Matthew Sandoval, and this is Lab 4, Oscillations. The contents of this lab are the introduction, experiment, code, discussions, and conclusions. The purpose of this lab is to compare the observed and predicted motions of a mass oscillating on a spring using the correct fundamental physical principles. Another purpose is to discuss relevant questions using associated graphs of the data, and the results are as follows. The energy principle is reflected through the results of the experiment, and the observed and predicted oscillations match closely with one another. There are a few fundamental physical principles and models that are relevant to this lab. Newton's second law, which allows us to derive the position and velocity update formulas, the energy principle, which states that the change in energy of a system is equal to work plus the shift in thermal energies. This formula allows us to connect the total change in energy of our system with various other energy formulas, such as kinetic energy, gravitational potential energy near Earth's surface, and spring potential energy. A few other formulas that are related to this lab are net force, position update, velocity update, and spring force. Also, it's important to note that potential energies are being considered for this lab because there are no surroundings. The first step of the lab is to download the associated oscillation video and upload it to the tracker. Once uploaded, I analyzed the massive motion on tracker, plotted the X and Y position data points into an Excel sheet, and this Excel sheet was exported as a CSV file for computation. I then edited starter glow script code in order to illustrate what the predicted motion of the mass is. I compared the findings of observed and predicted values, and I answered supplemental questions to make conclusions. Also for this lab, I had to assume there is no drag force, and I wasn't accounting for the thermal force. The images on the left of the slide show some of the setup for tracker as well as the initial conditions found using tracker. As far as the system of this lab goes, it consisted of the earth, the spring, and the mass attached to the spring. There were no surroundings in this lab, which is important because since there are no surroundings, the work done on the system will equal zero. This means that we have to consider potential energies in our calculations in order to accurately reflect the transfer of these energies. The two equations below show the total change in energy of our system, which consisted of the change in kinetic energy plus the change in gravitational potential energy plus the change in the spring potential energy. The video on the left simply shows my tracker upload as well as the position points that I plotted for the mass. The code was split into two parts, initial conditions and iteration. The initial conditions of my computational model are shown below. I had to input a numerical value for the mass of the object attached to the spring. I changed my delta t to the frame dt from tracker. Also had to upload the gravity constant, the spring constant, and the relaxed length of the spring. The right of the screen shows the formulas for kinetic energy, gravitational potential energy, spring potential energy, and the change in energy of our system. This code was created using the equations shown in the introduction portion of this lab. In the iteration of my computational model, I set the while loop to persist for as long as the video and tracker was. This creates less discrepancies between tracker and the code. Each iteration updates the initial energies as the forces we are working with here aren't constant. The variable fgrav was calculated using the gravity vector, which is 0, negative mg, 0. The spring force was calculated using the correct spring force equation, and fnet was calculated using the addition of all forces. Also, in each iteration, the ball velocity and ball position are updated using the velocity and position update formulas as derived from Newton's second law. The energies are also updated, and they use the same equations as in the initial conditions of the computational model. Here are the video and graphical results of my computational model. The graph on the top displays the change in energy versus time of the various energies occurring within the oscillating motion. The two graphs on the right compare the computational model, which is the predicted motion, and the experiment model, which is the observed motion, in red. The computational model is in blue. The graph on the top displays their x positions and how they line up, and the bottom graph displays their y positions. For the most part, the computational model and the experiment model have similar x and y position values, although they do differ slightly more on the y position values than they do in the x. These reasons will be explained further on in the discussion. To break down a bit about what each graph is really showing, on the energy graph, the potential energies of the spring in green and the gravity in red oscillate in opposite directions, which means they have opposite signs. These energies, combined with the kinetic energy in blue, all add up to zero at any given time step. This should be the case since the change in energy, which was depicted in orange of the system, is shown to be zero, and it should be zero according to the energy principle. On the position versus time graphs, the x and y position graphs for both the observed model in red and the predicted model in blue line up close enough to denote a successful computational model. There were, however, a few errors that contributed to the y position of the graph not being as accurate. Possible sources of error for both graphs include the computational model not accounting for drag or heat exchange, and other energy types may have been present that aren't relevant to the current physics topics. There are two important questions that I need to address for this lab. The first is the energy principle justified in this model? The answer to that is yes. The energy principle essentially states that the total amount of energy in the system will remain constant. As explained earlier in the discussion section and shown in the graph to the right, At any given time, delta E remains constant at 0. This is further proven or supported by the oscillations of the other energy types, which add up to 0 at the same time steps. After calculating and comparing the oscillation periods for both the x and y position versus time, I noticed the oscillation averages have a difference of about 0.3 seconds. This is a large difference which has certain impacts on the formulas that rely on the times of these oscillations, which include the spring constant equation. This would have an effect on the spring force and potential energy, which can explain the observed versus predicted graph discrepancies. These differences are most likely due to forces and energies not being considered, as well as human error and tracker.